Have you ever noticed how delving deeper into quantum mechanics almost inevitably leads to like more and more philosophical questions? You know, it's like every answer just unveils like a dozen new mysteries about reality itself.
Yeah, it definitely has that effect. The deeper you go, the more you realize how much we don't know.
Exactly. So today we're going deep, really deep into one approach that tries to grapple with these like fundamental quantum
Oh, this
puzzles.
is going to be good. I love a good deep dive.
Me too, especially when it involves things that make you question like the very fabric of reality. We're talking about the consistent histories interpretation.
Consistent Histories, or CH for short. That's a fascinating one.
It really is. And to make sure we're on solid ground, we're using excerpts from the Stanford Encyclopedia of Philosophy, a real authoritative source.
No, yeah, the essay. That's the gold standard for philosophy stuff.
Absolutely. Now, to our listeners who maybe identify as like philosophically inclined, why should you stick around for this deep dive?
Well, CH doesn't shy away from like the big philosophical questions that quantum mechanics throws at us.
It's like it dives right into the deep end of the philosophical pool. No floaties.
No floaties, exactly. We're talking about the nature of measurement, what it even means in the quantum world.
Which, let's be honest, is still kind of a mystery in many interpretations.
Big mystery. Then there's the question of reality itself. Is there like a single objective quantum reality?
Or are we talking about multiple realities, parallel universes, all that jazz?
And what about logic? Do our everyday rules of reasoning even apply in this weird quantum realm?
I mean, some of the stuff we see in quantum mechanics seems to defy logic as we know it.
It does. And of course, there are those pesky quantum paradoxes, the ones that seem to like undermine our understanding of everything.
Like Schrodinger's cat, that poor hypothetical feline.
Yeah, Schrodinger's cat. Always both alive and dead, at least until we peek in the box, which is where things get really weird.
Super weird. But CH actually tries to give us like a more logical framework to make sense of all this.
It's less about adding more interpretations and more about like giving us a way to reason about the quantum world in a consistent way.
Exactly. So our mission today is to break down the core ideas of CH. We want to get a grip on its key concepts, and most importantly, see how it tries to untangle some of those mind-boggling quantum paradoxes.
Sounds like a plan. Let's get paradoxical.
So what was the initial motivation behind developing CH? What problem was it trying to solve?
Well, often the starting point, I think, is the sort of like unease or even outright confusion that many people, physicists included, feel with like the standard textbook presentation of quantum mechanics.
It's like you learn the equations, you can solve the problems, but you still walk away feeling like, wait, what did I just learn?
Exactly. It's like you're missing the bigger picture, the underlying story.
Yeah.
And a persistent pain point, a real sticking point, has been the role of measurement.
Measurement, the bane of many a quantum physicist's existence.
In many interpretations, measurement seems to play this like special, almost magical role. It's like this external intervention that forces the quantum world to choose to collapse into a definite state.
Right. But the underlying theory doesn't really explain how or why this collapse happens.
Exactly. It's like poof, it's collapsed. But why? How? No one really knows. And that's where CH steps in and says, hold on a minute, maybe we need a different perspective.
So CH offers a radical departure from this measurement-centric view.
Yeah, pretty radical. In CH, measurement doesn't hold this like privileged fundamental position. It's not seen as this distinct process that's somehow different from any other quantum interaction.
So what takes center stage in CH?
Well, instead of focusing on measurement as the source of all quantum weirdness, CH puts probability front and center. It's all about probabilistic time dependence.
Probabilistic time dependence, meaning the way quantum systems evolve over time is inherently probabilistic, not just during measurement.
Exactly. Probability isn't something that's just tacked on for measurement. It's baked into the very fabric of how quantum systems change.
Okay, so rather than this deterministic evolution that's punctuated by these probabilistic collapses during measurements, it's like everything in the quantum world is constantly evolving probabilistically.
That's a good way to put it. And these probabilities aren't just random, they're governed by rules, like the Born rule or its extensions.
So we have these rules, these mathematical laws that govern the probabilities of different quantum events happening.
Precisely. But to make sense of these probabilities, to apply them in a way that doesn't lead to contradictions or paradoxes, we need to introduce a key concept: frameworks.
Frameworks, that sounds important. What exactly are frameworks in this context?
Think of a framework as like A well-defined space of possibilities, a set of allowed questions you can ask about a quantum system where we can assign probabilities in a consistent way.
Okay, so it's like setting the stage, defining the rules of the game before we start talking about probabilities.
Yeah, you need the right playing field before you can start playing. Technically, a framework is what we call a projective decomposition of the identity, or PDI.
PDI, it's always with the acronyms.
I know, right? But don't let the jargon scare you. A PDI is basically a set of quantum filters, mathematically these are called projectors, that allow us to divide the system's entire space of possibilities into distinct, non-overlapping categories.
Okay, so we're taking all the possible realities of a quantum system and sorting them into neat little boxes.
Sort of. Each projector is like a filter that only lets through certain states, certain realities that have a specific property. And when you add up all these filters, you get the identity operator, which represents the whole range of possibilities.
So it's like saying, okay, here are all the things this quantum system could be doing, and now let's divide them into these mutually exclusive categories.
Right. Like if our system is a coin, one projector could be for heads and another for tails.
And since a coin can't be both heads and tails at the same time, these projectors don't overlap.
Exactly. They're mutually exclusive and they cover all the possibilities. That's the key.
Can you give us a more quantum example,
Yeah.
for the physics nerds in the crowd?
Of course. Let's take our favorite, the spin-half particle.
The spin-half particle, always a crowd pleaser.
A simple PDI for its spin could be z plus z. Here, z plus is the projector for spin up along the z-axis, and z is for spin down along the z-axis.
So these projectors are like asking the particle, hey, is your spin up or down along this particular direction?
Yep. And since the spin can't be both fully up and fully down along the same axis at the same time, these two possibilities are mutually exclusive.
And they cover all the possibilities for spin along that axis. So that's one framework, one PDI, for describing the spin of our little particle.
Exactly. Now, why are these frameworks so crucial to CH?
Yeah, why all the fuss about frameworks?
Because here's the golden rule, the absolute key rule in CH. Any reasoning you do, any description you make about a quantum system has to be done entirely within a single framework.
You can't mix and match.
No mixing and matching allowed. You can't combine properties or probabilities from different frameworks and expect things to make sense.
Sounds strict. What makes frameworks incompatible with each other?
To get that, we need to dig a little deeper into how quantum properties are represented mathematically.
Oh boy, here comes the math.
Don't worry, it's not too bad. In quantum mechanics, a property like the spin is up is associated with a subspace of a mathematical space called Hilbert space.
Hilbert space? Sounds fancy.
It is pretty fancy, but the main idea is that each point in Hilbert space represents a possible state of the quantum system. And a property is like carving out a particular region, a subspace, of this Hilbert space.
So it's like saying all the states in this region have this property and all the states outside this region don't.
Right. And these subspaces, these regions, are represented by our projector operators. Remember those filters we talked about?
Yeah, the ones that only let through certain states.
Exactly. Now, if you have a classical property, you can define a function that's like a yes-no question. Does the system have this property? Yes or no, 1 or 0.
Like, is this apple red? Yes or no?
A quantum projector acts in a similar way. It's like asking a yes-no question about a quantum property.
Okay, so it's a mathematical tool for identifying which quantum states have a particular property.
Now, what about negation? If I have a projector P for a property, how do I represent not P, the opposite of that property?
In classical logic, we just slap a knot in front of it, right?
In quantum mechanics, we do something similar. Negation is represented by the identity operator, which is like the everything operator, minus the original projector, IP.
So it's like taking the whole set of possibilities and removing the ones that have the original property. What's left is the knot of that property.
That's a good way to think about it. And here's where things get really interesting, especially from a philosophical point of view.
Uh-oh, I sense a philosophical curveball coming.
When we talk about logical connectives like and, and, or in quantum mechanics, things get a little tricky. These combinations are only well-defined if the projectors involved commute.
Commute, you mean like in math, where the order of multiplication doesn't matter?
Exactly. If two projectors, let's call them P and Q, commute, meaning PQ is equal to QP, then their product PQ is also a projector, and it represents the A and D of the two properties. Similarly, P plus PQ represents the OR.
So if the projectors commute, we can talk about property P, A and D, property Q, or property POR, property Q.
But, and this is the crucial part, If the projectors don't commute, if PQ is not equal to QP, then these AND and OR combinations become undefined or even meaningless within the consistent histories framework.
Meaningless, not just false. That's a big difference.
Huge difference. A false statement still has meaning. We understand what it's claiming, even if it's wrong, but a meaningless statement in the CH view doesn't even have a truth value.
It's like asking, what is the color of jealousy? It's a question that just doesn't make sense.
Exactly. And its negation is equally meaningless.
So we can't even say jealousy is not blue because the original question was already nonsensical.
Precisely. So let's go back to our spin half particle.
Back to the trusty spin half particle.
If we try to talk about its spin along the z-axis and its spin along the x-axis simultaneously, we run into this issue.
Because those spin components don't commute.
Exactly. The projectors for spin up along z and spin down along z don't commute with the projectors for spin up along x and spin down along x.
So I can't say something like, the particle's spin is up along z and d up along x, and expect that to be a meaningful statement within CH.
Nope, not at all. Those properties are incompatible. They can't be combined in that way.
And this leads us to the single framework rule, right? This seems like a pretty big deal in CH.
It's the cornerstone of the whole approach. The single framework rule says you have to stick to one framework, one PDI, for any reasoning you do about a quantum system. Combining things from different incompatible frameworks is a big no-no.
So it's like saying, pick your framework, stick to it, and don't try to sneak in concepts from other frameworks.
Exactly. It's about maintaining consistency in our descriptions.
You mentioned that the single framework rule has like 4 guiding principles associated with it: liberty, equality, incompatibility, and utility. Can you quickly go over what those mean?
Absolutely. Liberty is like the freedom of choice. Physicists can choose whichever framework is most useful for the problem at hand. There are no restrictions on which frameworks you can use as long as you respect the other principles.
So you're free to choose your weapon, so to speak.
As long as you use it responsibly. Then there's equality, which says no framework is inherently better or truer than any other. They're all equally valid ways of describing the quantum world.
No framework discrimination.
Right. They're just different lenses through which to view the same quantum reality. Incompatibility, as we've discussed, is the crucial constraint. It's like the no mixing and matching rule. You can't combine descriptions or probabilities from incompatible frameworks without running into trouble.
Don't mix your metaphors or your frameworks.
And finally, utility suggests that the choice of framework should be guided by the question you're trying to answer. Some frameworks will be more useful for addressing certain questions than others.
So it's like picking the right tool for the job.
Precisely.
So we have frameworks for describing quantum properties at a single moment. How does the concept of quantum histories extend this to include the evolution of the system over time?
A quantum history is basically a sequence of events, where each event is a quantum property that the system possesses at a particular time.
Like a timeline of the system's quantum journey.
Exactly. And just like we have frameworks for properties at a single time, we also have families of histories. A family of histories is a set of possible, mutually exclusive timelines, each representing a different way the system could have evolved.
So it's like saying, here are all the possible paths this quantum system could have taken.
And each path, each history, is represented by a sequence of projectors, one for each event in the timeline.
And these histories are mutually exclusive, meaning the system can only follow one of these paths.
Right. And just like with single-time frameworks, the projectors in a family of histories have to sum up to the identity operator, meaning they cover all the possibilities.
So we're still being very thorough, accounting for every possible way the system could have evolved. But how do we assign probabilities to these different histories?
That's where the generalized Born rule comes in. It's basically an extension of the standard Born rule to histories. It involves calculating a chain operator for each history, which encodes how the system's state changes at each step along that timeline. The trace of this chain operator, combined with its adjoint, gives us the probability of that specific history occurring.
Trace. Adjoint. Those are some more mathy terms.
I know. But the key idea is that we have a mathematical rule for calculating the probability of each possible history, given the system's initial state and how it evolves over time.
So we have these possible histories, and each history has a probability associated with it.
Exactly. But there's a catch. These probabilities only make sense if the family of histories satisfies certain consistency conditions.
Consistency conditions, like rules that make sure the probabilities don't lead to contradictions.
Precisely. These conditions ensure that the probabilities within a family of histories behave in a logically coherent way. For example, the probabilities of all the possible histories have to add up to 1, just like in classical probability.
Makes sense. So these consistency conditions act like a sanity check on our probabilities.
And interestingly, for histories that only involve 2 points in time, like an initial state and a final measurement, these consistency conditions are always automatically satisfied.
So that aligns with the standard Born rule in basic quantum mechanics.
Exactly. Now, one of the most striking aspects of CH is how it deals with measurement.
Yeah, measurement is always a hot topic in quantum mechanics.
In CH, measurement isn't treated as some special fundamental process. It's analyzed as a regular physical interaction, just like any other.
So no need for this mysterious wave function collapse.
No need for collapse. Measurement is just another quantum interaction, governed by the same rules as everything else.
Which brings us to those infamous quantum paradoxes. How does CH tackle these head-scratchers? Starting with the classic, Schrödinger's cat.
Ah, Schrödinger's cat. That thought experiment really captures the weirdness of quantum superposition.
It does. So how does CH approach this seeming paradox?
In CH, the cat being in a superposition of alive and dead doesn't mean it's simultaneously both or neither.
So it's not like some zombie cat that's half alive and half dead.
No zombie cats allowed in CH. The paradox arises from trying to apply classical concepts of alive and dead to a system that's in a quantum superposition.
So we're trying to force-fit a classical description onto a quantum situation, and that's where the paradox comes in.
Exactly. In CH, the projectors for alive and dead are incompatible with the projector that describes the cat's superposition state. So within a consistent framework for describing the cat, it's not meaningful to say it's both alive and dead at the same time.
It's like those properties, alive and dead, just don't make sense in the context of that superposition state.
Right. They don't fit into the same framework.
What about the Paris-Mermin square? That's another one that really messes with your head.
The Paris-Mermin square is like a quantum logic puzzle. It involves trying to assign definite values to certain spin measurements, and it leads to a mathematical contradiction.
Yeah, it's like quantum Sudoku gone wrong.
CH resolves this paradox by pointing out that the contradiction arises from mixing frameworks.
We're being sneaky and switching frameworks without realizing it.
Exactly. Some of the spin measurements in the square commute, so you can talk about them within a single framework. But others don't, and that's where the trouble starts.
So the paradox is like a trick, a sleight of hand, where we're unknowingly jumping between incompatible ways of describing the system.
Right. We're breaking the single framework rule.
Okay, what about those wave-particle duality experiments, like the double-slit experiment or the Mach-Zehnder interferometer?
Those are classics, showing how quantum objects can act like both particles and waves.
Yeah, but how can something be both a particle and a wave? It's mind-boggling.
The apparent paradox comes from trying to know both which path the particle took, a particle-like property, and whether it exhibits an interference pattern, a wave-like property.
So it's like wanting to have our cake and eat it too. We want to know both where the particle is and how it's behaving like a wave.
And according to CH, those desires are incompatible. If you choose a framework that lets you talk about the particle's path, you lose the interference pattern.
And if you choose a framework that shows the interference pattern, you can't say anything about the particle's path.
Exactly. You have to pick one or the other.
No compromise. Okay, let's tackle the big one, EPR and the related Bell inequalities. This one gets into the heart of locality, one of the most fundamental concepts in physics.
EPR and Bell. Now we're getting into the heavy stuff. The apparent non-locality, this spooky action at a distance where measuring one particle seems to instantaneously affect another one far away, arises from our classical assumptions about reality.
Like the assumption that particles have definite properties even before we measure them.
Exactly. In CH, these assumptions are shown to be incorrect in the quantum realm. Take the singlet state, for example, a pair of entangled particles with their spins correlated in a very specific way.
So their spins are linked, even if they're far apart.
The key insight from CH is that the singlet state's projector doesn't commute with the projectors for individual particle spins along a given axis. So within CH, it's meaningless to say that both particles have definite spin values along, say, the z-axis before we measure them.
So those properties aren't well defined until a measurement takes place.
Right. And the violation of Bell inequalities, which has been confirmed experimentally over and over, shows that this classical view, this idea of pre-existing definite values for all properties is simply not how the quantum world works.
So those experiments aren't necessarily demonstrating spooky action at a distance, but rather they're showing that our classical intuitions about reality break down at the quantum level.
Precisely. Consistent histories gives us a way to understand these correlations without resorting to faster-than-light signaling.
So CH is like, relax, there's no need to abandon locality. It's just that reality is more nuanced than our classical brains are used to.
Exactly. Within CH, there's a principle called Einstein locality. It states that an isolated system's objectively real internal properties don't change because of something you do to another system that's not interacting with it.
That sounds reasonable. What does it mean for a property to be objectively real in CH?
That's the key point. What counts as an objectively real property depends on the framework you're using.
Frameworks again. Always back to frameworks.
Always. Because the singlet state's overall projector doesn't commute with the projectors for individual particle spins, we can't consistently talk about both particles having definite spin values along all axes simultaneously. It's just not a meaningful description within a single framework.
So we're back to this idea that you can't just mix and match properties from incompatible frameworks. That's a recurring theme in CH.
It really is. Now, we've established that the quantum world, at least according to CH, is fundamentally probabilistic. But the world we experience every day seems pretty deterministic. How does classical physics, with its predictable laws, emerge from this underlying quantum fuzziness?
Yeah, good question. If everything is probabilistic at the quantum level, why does the world seem so predictable at our macroscopic level?
That's where quasi-classical frameworks come in. These are frameworks that, while still quantum in nature, involve projectors that effectively commute with each other at the macroscopic level.
So it's like the quantum fuzziness gets smoothed out when we zoom out to the macroscopic world.
Sort of. Think about it. Macroscopic objects are made up of trillions upon trillions of atoms, each behaving quantum mechanically. But all those tiny quantum fluctuations tend to average out at the macroscopic level.
So our classical world is like a blurry picture of a fundamentally quantum reality.
That's a good analogy.
What about measurement itself? If it's not this special process that causes wave function collapse, how does CH analyze what's happening when we make a measurement?
In CH, a measurement is just a physical interaction where we amplify a microscopic property into a macroscopic outcome that we can observe.
So it's like using a microphone to amplify a faint sound.
Exactly. It's about making something small and quantum into something big and classical.
And this approach helps CH address the two notorious measurement problems.
Precisely. The first problem, MP1, is how to describe the macroscopic outcome of a measurement in quantum terms.
Like, how does the pointer on a dial get to a definite position?
CH tackles this by using those quasi-classical frameworks we talked about to describe the measuring apparatus.
So we treat the measuring device as a macroscopic object that can be described using a framework where quantum fluctuations are essentially negligible.
Right. And the second problem, MP2, is how that macroscopic outcome relates back to the microscopic property we're trying to measure.
So how do we connect the position of the pointer to the spin of the particle?
CH uses different families of histories to address MP1 and MP2 separately. One family might describe the interaction between the system and the apparatus, showing how they become correlated. Another family might focus on how we infer the original microscopic property from the final macroscopic reading.
So it's like using different lenses to look at different aspects of the measurement process.
And the choice of which lens, which framework to use, depends on what question we're asking.
It's all about picking the right tool for the job. So CH doesn't really have a measurement problem in the traditional sense because it doesn't elevate measurement to this special mystical status.
Exactly. It's just another quantum interaction, albeit one with important consequences for what we can observe.
What about wave function collapse? That's always presented as a central part of measurement in standard quantum mechanics.
In CH, wave function collapse is viewed as a calculational tool, a way to update our probabilities based on new information.
So it's not a real physical process that's happening to the system.
Not in a CH view. It's more about updating our knowledge, our description of the system, within a particular framework.
So it's like revising our beliefs based on new evidence rather than the system itself suddenly jumping into a different state.
That's a good way to put it. And speaking of information, how does CH relate to the burgeoning field of quantum information?
Quantum information is a hot topic these days. Lots of exciting stuff happening there.
And CH has a lot to say about it. Because CH uses standard probability theory within a single framework, It provides a very natural way to apply classical information theory to the quantum realm.
So we can talk about things like bits and entropy in the quantum world, just like we do in classical information theory.
Exactly. And this allows CH to address some of the deep questions that John Bell raised, like whose information is being talked about, and information about what.
Yeah, those are important questions.
In CH, information is fundamentally about quantum properties or histories, and it's something that can be possessed by anyone who can build the right measuring devices and interpret the outcomes using consistent quantum principles within a chosen framework.
So it's like saying information is objective in the sense that it's tied to these quantum properties and frameworks, but it's also subjective in the sense that it depends on who's doing the measuring and interpreting.
Right. It's a nuanced view of quantum information that avoids some of the more philosophical pitfalls of other interpretations.
Now, as with any interpretation that challenges the status quo, CH has faced its share of criticism. What are some of the main criticisms that have been leveled against it?
Well, some critics have argued that CH is internally inconsistent, that it leads to contradictions.
So they're saying, hey, you claim to be consistent, but you're not really.
Exactly. But proponents of CH counter this by saying, look, you're misinterpreting the framework. As long as you stick to the single framework rule and carefully distinguish between consistency conditions for histories and the logical structure of the framework itself, there are no contradictions.
So it's all about being rigorous and consistent in how you apply the rules.
Right. Another criticism is that the single framework rule itself is too restrictive. Some argue that it's too different from classical logic and that it limits what we can say about the quantum world.
So they're saying CH is like putting us in a philosophical straitjacket.
Sort of. But the CH response is that this rule is necessary because of the non-commuting nature of quantum properties. It's not about restricting our ability to describe the world, but rather about ensuring that those descriptions are consistent and don't lead to logical paradoxes.
So it's like, yes, the rules are different in the quantum world, but that's just how it is.
Exactly. And then there's the unicity of the world objection.
Unicity of the world, meaning there should be just one true state of affairs, one objective reality at any given time.
Right. This objection says CH is wrong because it allows for different frameworks and therefore different descriptions of reality.
So they're saying, pick a framework, any framework, but stick to it. Don't tell me reality depends on which framework I choose.
Exactly. But CH embraces this kind of framework dependence. It says truth, at least at the quantum level, can be framework dependent. And it argues that the success of classical physics and our experience of a seemingly unique world are explained by the existence of these quasi-classical frameworks that we naturally use at the macroscopic level.
So CH is like, yeah, there are multiple frameworks, but don't worry, they all converge to the same classical reality at the macroscopic level.
Right, and that convergence is what gives us the illusion of unicity in our everyday world.
So to sum up for our philosophically inclined listeners, Consistent Histories presents a probabilistic worldview where quantum properties are described within well-defined frameworks called PDIs.
And you can't just mix and match properties from incompatible frameworks. That's the single framework rule.
Right. And this rule leads to a quantum logic that can be quite different from our classical intuitions. CH provides a framework for understanding quantum histories, how systems evolve probabilistically over time, and it offers potential resolutions to those pesky quantum paradoxes, often by pointing out where we're implicitly breaking the single framework rule or trying to force classical concepts onto quantum situations where they don't apply.
And it does all this without invoking any special role for measurement or wave function collapse.
Exactly. Measurement is just another quantum interaction in CH. And it provides a really interesting perspective on the philosophical foundations of quantum mechanics, questioning the very nature of reality and truth.
It really does. It's a thought-provoking approach that forces you to re-examine some of your deepest assumptions about how the world works.
Absolutely. For listeners who want to delve deeper into CH, we highly recommend checking out the Stanford Encyclopedia of Philosophy entry on consistent histories. It's a great starting point.
And there's also the Consistent Histories homepage online. You can find a lot of resources and discussions there.
Now, for a final thought to leave you pondering. If reality itself is indeed framework dependent at the quantum level, what implications might that have for our understanding of truth and objectivity, even in our everyday macroscopic world?
Does CH offer us a path towards a more coherent worldview that can encompass both the quantum and the classical? Or does it fundamentally challenge our classical intuitions in a way that requires us to completely rethink our notions of reality and truth.
These are the kinds of questions that make the foundations of quantum mechanics such a fascinating and endlessly intriguing subject.
And that's why we love to explore them.
Exactly. And we'll keep exploring them in future deep dives. Until then, keep those philosophical gears turning.
And keep questioning everything.